in this lecture and the future ones that I'm going to give. So like the big picture is I'm an energy thermal fluids guy. I took mechanics of materials in the 20th century as an undergrad. The last time I taught mechanics of materials, I assure you, none of you were born yet. It was like years ago. However, I do this almost every day in my capstone class. And before I taught capstone, I started a whole bunch of different companies. In fact, students always talk about in their feedback, Traum talks about his startup companies too much. Let's startup companies, Traum, more like lecture content. So I'll try to not talk about the startup companies. But speaking of startup companies, we are working right now with the Army to start a company that is basically creating a device that lifts a camouflage net over an Army vehicle so that the soldiers don't have to like jump out and do it by hand. And it's incredibly interesting mechanics and materials problem because there's just this single beam that's basically supporting this 100+ pound camo net. And we're having to like rotate the beam to lift the net up over the vehicle. And so in capstone on basically a daily basis, we're doing mechanics and materials calculations to get that system as light as it can possibly be so that the Army guys aren't having to carry around this big heavy thing. But to still make it functional and not, fail when we put loads and stuff on it. So the big picture here is what I'm hoping to impart on you guys is sort of a sense of like how this stuff that we've been learning for the past, it's like 7 or 8 weeks, translates into like the real world, right? So hopefully that's the spin that I provide. So I'm gonna see if this works. We're talking today about, I think, I've already messed it up more than once. Let's see if we can get the pen back. There it is. Okay. So that's annoying. We're talking today about section. I can write up here, but I can't write down here. 5.2. There we go. 5.2, which is, what is going on here? Relationships between loads, shear, and bending moments. And I'm going to have to keep pushing this button, bending moments. Okay. And kind of the big picture here, which Ting has alluded to already. So the big picture is basically we need to come up with shear and bending moment diagrams because that's what you use to solve real world problems, right? You need to basically identify where the most likely spot is that a mechanics member is going to fail. And that spot is most likely to be the place where there's the maximum bending moment or the maximum shear. And because we're engineers, some people say I'm an engineer and I'm lazy and I like to do things a particular way that makes it easy. I say, hey, we're engineers and we like to do things in the best, most efficient way so that we're not wasting energy and brain cycles on something that's not important. So if you figure out the spot where the maximum bending or the maximum moment is, the maximum shear, the maximum moment is, and you've determined that the member will not fail under that particular set of conditions, then it won't fail anywhere else, right? So we're basically not being lazy, but being efficient. We're trying to find the spot where the member is the weakest or where the chances of failure are the highest. Make sure that it doesn't fail at that spot, and then we know that it's good to go for the rest of the device or the rest of the member. So there is no need to evaluate every location on a mechanical member to determine whether it's going to fail or not. If fail doesn't occur at that maximum shear or maximum bending location, then it's not likely to occur anywhere else. And so you can basically be like the smartest person in the room, right? Where you're sitting down and everybody's giving their design reviews and presentations, and you can actually like do the calculation and show this isn't going to fail. And people with their finite elements and their calculators and all that stuff, like they're wasting a ton of energy, and you basically solve the problem with a single calculation. So that's where we're going with this, is just trying to make this as easy as possible for you to get to the right answer, which is this part is not going to fail under these conditions. Next question. And then Dr. Ting pointed this out. You guys already know how to do shear diagrams and bending moment diagrams because presumably you took statics. It's a prerequisite for this class. However, the way that you were taught to do it in statics is inefficient, is probably the word that I use. I actually wrote the word crap on my notes, like it's crap, but then I thought, oh, that's probably offensive and I shouldn't say that. So anyway, scratch that from the record. We're going to teach you a better way to do it. So we're going to start out with, and I should mention this. So engineers like to do this all the time, right? Is that we'll take like some steady state problem. And again, I'm an energy thermal fluids guy, so I take little lumps of fluid all the time and do this analysis on them. But we like to take some sort of kind of continuous problem and break it up so that we can start taking derivatives and integrals by looking at like a finite section or a finite element of like a bigger continuous piece of material. And so the big goal, see if I can get this to right this time. The big goal is to come up with a more efficient, there we go, more efficient approach to bending, shear, and moment diagrams. I have no idea why that just changed to red. Okay. So we're going to start out with this section of beam here, and notice that it has this load on it. It's this sort of continuous function, which we just call W of X, which we just call W of X was build. Okay, so we have this section, and we're going to basically just take this tiny section, which is delta X. We're going to start out with X equals 0 at this A location. We're going to make X go to the right, and then delta X. And we're going to do basically a free body diagram on this little section, which has a thickness of delta X. There are kind of two built-in underlying assumptions here, engineering assumptions. The first one is that we have no concentrated force. And the second one is that we have no couples applied. And why those are important will become apparent in the future, but you can see here, there's this force and there's this couple, but they are intentionally outside of where I've selected this section C prime, right? So I'm doing that on purpose for purposes of the derivation. So with those two assumptions, we're going to do a free body diagram. And I'm, again, assuming that you guys have taken the class up until now, and so you know how to determine the directions of all the shear stresses, bending moments, et cetera. So I'm not going to run through that. But I am going to go through the free body diagram so that you can see where it comes from. And there is a negative sign that Dr. Ting and I disagree on. So I'm going to do it the way that she said, is because the textbook has an error in it, right? There's a negative sign that shouldn't be there. Yeah. So I'm going to try to do it the way that she's described it. So if there's a weird negative sign that sort of disappears, I'll have her explain where that goes. So we've got some of the forces in the Y direction. By the way, that's the positive Y direction. So we've got some of the forces in the Y direction because the system is static, that equals 0. And we're just going to go through and add everything up. So I've got positive V, I've got negative WX delta X. And where does that come from? Well, there's W, and then it's over a distance X. So that's the load associated with that sort of unknown function of W. And then we're going to have minus V plus delta V. And my favorite thing to do in engineering is to cross out all the stuff I don't need. So I'm going to notice that those two V's cancel each other. And then I'm going to be left with delta V is equal to WX delta X. And that's my first equation. So we'll call that number 1. And now we get to do calculus, which is, I'm going to say, okay, this is delta V over delta X is equal to W of X. And that looks an awful lot like a derivative, dV dx. And if I then take the limit as dx goes to 0, I end up with the expression that I want, which is basically that that is going to get annoying really fast. dV dx is equal to Wx. Okay, so now that we've got the forces mostly figured out, let's do the moments. And how do I get to the next slide? There we go. Okay, so we're going to do, you know what? I'm going to turn off the laser pointer because I think the laser pointer is actually causing me to not be able to write with a pen. So let's turn that off. Okay, so we're going to do some of the moments around the point C prime. And because we're in a static situation, that's equal to 0. And I'm going to run through this minus V delta X minus M minus Wx delta X over 2 plus M plus delta M. Okay. And then I'm going to go through and I'm going to cancel things out that are the same. So for example, this moment goes and that moment is delta M is equal to V delta X plus Wx over 2 delta X squared. And this is going to be my second key equation. So I'm now going to basically take the limit as delta X goes to 0. So now I'm doing calculus. And what I end up with, if I fight my way through this, is dm dx is equal to V of X. And so this is going to be my second key equation that I'm going to use to figure all this stuff out. Okay, so the thing, which this is my interpretation, is the slope of the bending moment diagram is equal to the shear force at a point. So this is basically saying in words what the equation number 2 states in mathematical numbers. Okay, so let me move to the next slide. So now we're going to start to visually look at these equations and try to interpret them. And remember, again, the big goal is, can we come up with shear and moment diagrams without going through all of the complexity that you guys had to go through in statics? So I wrote in my notes here, calculus is awesome. So let me see if I can write that. Calculus is awesome. And what I mean by that is that we can basically construct shear and bending diagrams, bending moment diagrams, by inspection and a little bit of calculus knowledge. So just remembering what the definition, calculus, what the definition of a slope is, what the definition of an integral is, and so forth. So if you look at kind of this progression from A to B to C, here's my beam. It's supported by a pin on one side and by just a roller on the other side. And I've got this distributed load across the beam that just has, again, some arbitrary function. W is a function of X. X starts here and goes that way. And what I'm wanting to do is just take that shape and kind of map what it's doing onto my shear diagram and my moment diagram. And there are a couple of key points that we're basically looking at in the figure that show us how this mapping works. So if we remember that first equation, dvx is equal to wx. And if we remember the second equation, d moment dx is equal to v, we'll put an x there. If I look at this function of x, and then I remember that that function of x is just the derivative of the shear diagram, I can figure out basically what the shear diagram is doing just by interpreting the derivative. So for example, at this spot to the far left, the function w of x is 0. And so we expect the slope of the shear diagram to be 0, right? Because wx is 0 there, so the slope is going to be 0. And then what's happening is that we've got this like ever increasing value of wx. And as a result, we have this ever decreasing magnitude of the slope of the shear diagram. So, and it says here, w is negative increasing and slope is negative increasing. So if we then translate from the shear diagram to the moment diagram, it's basically the same thing, right? We're just sort of integrating in our minds. And so if we look at this point A and we go all the way down to the moment diagram, A was 0 in terms of the function W. On the shear diagram, it's just a constant flat value with a slope of 0. And on the moment diagram, we're now basically taking a second derivative in our minds. And we see there's just kind of a positive linear slope right at the beginning of that spot A. And then as we look at point C and point D, you can see the slope in the shear diagram is ever decreasing, or the value of the shear diagram is ever decreasing towards 0. And so the slope of the moment diagram is decreasing until it basically hits a maximum where the slope there is 0. And then this value goes negative and the slope here starts to go negative as a result. So hopefully you're interpreting or seeing what I'm trying to convey, which is the idea that if you look at the loading function and then integrate it in your mind, remembering that the derivative of the shear diagram is the loading diagram, and then integrate it again in your mind to remember that the derivative of the moment diagram is that the moment diagram is the derivative of the shear diagram, you can just by construction back out what all these different diagrams look like. So let me pause for a second and just check because I'm pretty sure I did that right. So is that clear that we're basically just looking at derivatives and integrals of each other? Okay, I've seen people nod, so that's awesome. That means I did something well. Okay, so because we've got these derivatives and because calculus is awesome, we can basically, what I described it as, we can also go in the opposite direction. So we talked about derivatives, direction. Once we have derivatives, we can go in the opposite direction and take integrals. So if we start out with dv dx is equal to wx, so this is my equation that connects the load on a member to the shear diagram of a member, I can just, there we go. I can do this, right? Which is just taking dx to the other side of the equation. This is like engineering calculus, and do an integration where I'm integrating on the left side from VC to VB. What does that mean? Well, C is this spot and B is that spot. And so I'm just integrating the shear from that spot to that spot. And then on the other side of my equation, I'm integrating this loading function from C to D. So this is going to be X sub C to X sub D. And what I end up with is just VD minus VC is equal to integral of WX over that region. And so what this translates into in terms of words, right, is I can say the change in shear force, or shear, let's just call it shear, change in shear from D to C is equal to the area under the distributed load. And basically, again, the goal here is to try to give you guys a tool set to be able to figure out how to construct these diagrams without going through all of the steps that you learned in statics. And so this is a very powerful tool because if you know the value of shear at one spot and you know the loading on the beam, you can use this equation to get the value of the shear at another spot. And you can use that extra spot where you know the value to start constructing key points from the diagram. Okay, so by a similar token, we've got this figured out. By a similar token, I can take this equation and I can integrate it in the same way. So I'm going to say dm dx is equal to vx. And I'm going to do the same trick, which is I'm going to move everything that's integratable to one side of the equation, mc md dm. And over here, I'm going to go from xc to xd, and this is going to be vx dx. And so I probably need to move to the next slide because I'm going to run out of room. So let me do. Yeah, you figured out where the negative sign came from? Hey, I had a nightmare about this last night.
Go back. Go back to the
There.
So students, you can hear me, right? So the negative sign is because there's a positive here. Let me write it here. So this one is upward, so it should be positive, and so in the end, yeah, it worked.
The book is wrong.
The book is wrong. Yes.
The book is wrong. Okay, I'm absolved from my bad.
So in the previous, I told you the textbook is wrong, but I was a little confused. Yes. Just now I was like sleep deprived.
Yeah, no. So,
Yeah.
so to be fair, you told me the textbook was wrong.
Yeah, I told you yesterday the textbook is wrong.
Yeah, and I went through and I did not.
Textbook is wrong.
I did not spot that, and so
Yeah.
I just trusted you that negative sign wasn't there.
You asked me just, I was like, my brain.
But yeah, okay,
Yeah.
awesome. By the way, as a quick aside, I had a student yesterday tell me that their favorite moment in college is when faculty members disagree on something, because we try to project to you that we know everything, and Ting knows everything, but I know almost nothing. So when we have a disagreement about something and you guys get to see us banter back and forth, it sort of gives you a sense that we're people too, right? And we make mistakes, and I make more mistakes than probably anybody else. So anyway, now that we've figured out, and yeah, that's actually brilliant. So this plus sign is the result of this force being upwards, right? So they've actually drawn it in this diagram as upwards. And so when you add it together, it comes in as positive. And then when you do the math, it works out that there's no negative sign. So back to the original question from about 20 minutes ago. Is that okay? Awesome. We figured it out. It took us a little while, but that's what engineers do, right? So, okay. Let's see if we can get back to where we were. There we were. Okay. So I'd gotten this far, and I was about to basically take this equation one more step. So let's do that. Make sure that I know what I'm about to write. Okay, let's take it one more step. So what we end up with is that the moment at D minus the moment at C is equal to the integration across that distance of whatever the function of the shear is over that same distance. And so this is another important equation for the same reason. Yeah. Sure. I can even try to kind of write it here, but I was worried that I was going to run out of room. So this is MD minus MC, and that's going to be equal to basically the same thing. XC, XD, VX delta X. So, yeah. Yes, yes. So for the people at home, if you didn't hear the question, which is a brilliant idea, you could go right from the loading diagram to the moment diagram by just taking a double integral, right? We're taking that intermediate step so that we can get the value of shear if we need it. But you're right. We're just literally taking the same integral. Yeah, thanks for that. Yep. And then there was a question in the back. I switch back and forth. Like I noticed that about my own notes. I'm like, what's this M thing? Oh yeah, it's moment and it doesn't matter. So for me, it's either way, but I think the proper convention, and I'm looking at Tingen, is capital M for moment. I just scribble it fast. So lowercase m and capital M are the same thing. Okay, how we doing? Okay. I'm supposed to give, okay, let's see if we can power through this a little bit. Okay, so, all right, so we've got these two equations. Oh, I was gonna write what the interpretation of this one is, and let's get that one right. So the interpretation of this in words is that the change in the bending moment, and let me make sure I get it right, from D to C, I'm looking at my friend here in orange to make sure that I've written that the right way, D to C. I'm thinking about it. That for the folks at home listening on Zoom, we're debating D to C versus C to D because of the direction that we're moving. So the way that the integral is set up, I'm integrating from C on the lower side to D on the upper side. So as I do the subtraction, I don't want to say that like D is the higher value, but D is the value like on the top side of the integral. And so as I do the subtraction, that's what I mean by C to D. I'm basically subtracting, I'm starting at D and I'm subtracting C to get to that value. I don't know if that clears it up or makes it worse, but okay. Got it. Okay. Everyone at home good? Oh, there's some messages in chat and they're probably like, we want Ting back. And I can't. Okay, so questions about the negative sign, which we sorted out, and then questions about C to D. And nobody said we want Ting back, which I really appreciate. Thank you. So, okay. Oh, thank you. Someone says I'm doing great. You're being very kind. Okay, so now that we've got those two interpretations, how does this help us out? So how does this help? That's not what I wanted to have happen. Hang on, there we go. How does this help? So how many times you guys, I'm hopefully by now have all been interns at companies and you've sat in the room and the big, engineering manager walks in and you're doing some design review of some product that's about to be rolled out to the market. And some like random person in the back of the room after this whole big design presentation is over, raises their hand and they're like, it's not gonna work. And the boss is like, what? We spent $1 million and 70,000 man hours and blah, blah, blah. And the guy basically, or the person pulls up an envelope, right? And is like, here's a calculation that shows it doesn't work. And the whole thing gets trashed. Like it shouldn't happen, but it happens a lot in industry. And you guys want to at least be able to give the impression that you're the smartest person in the room. And this is one of those cool kind of tools that allows you to do that, right? So there's going to be all these people doing FEA, and you're telling me to go faster. I'm trying to tell a war story. Okay, I'll tell you guys a war story later. The point is you should be able to construct these shear and bending moment diagrams basically on the back of an envelope with the information that we're providing here. And you could presumably or hopefully catch big mistakes that people that use FEA and all kinds of other techniques did not catch because this is a very simple technique. So the kind of big takeaway message is if you know a few simple things. So if you know the bending moment at a few key spots. So the values, right, which you can get from like free body diagram. And if you know the boundary conditions. So for those of you who have survived like, calculus 2, boundary conditions at the end of a beam. From that information, you can draw shear diagrams using bending moment slopes. And once you've got that, you can use your shear diagram to find the maximum shear, we'll call them spots, maximum shear spots. And remember, these are the places where failure is most likely. So just imagine yourselves in the future, right? Some big engineering presentation. They give you a couple of bending moment locations, a couple of load values, and you're able just back of the envelope to go through and come up with shear diagram. And you realize that the maximum shear of whatever this thing is that's being designed, it will not survive the loads that they're putting on it, right? And somebody did FEA and they, hung a who knows, but it's all computational and it's wrong. So this is a quick way of being able to work out the right answer. And then you can take the bending moment at any location. Oop, that's the word location, but I did not write it very well. Let's see if I can do this. I'm scared to do that. Let's do this. There we go. Okay. Bending moment at any location. Nope. Okay. Ooh, did I just push a button I didn't mean to push? No, good. At any location can be found by taking the area. Taking area under shear diagram. So you can use this in both directions. Okay, so if you're like trying to sort of get your mind around like, Traum, what are you talking about? You're crazy. Yeah, sometimes. This is the distributed load diagram. This is the shear diagram. And this is the bending moment diagram. And we already showed on the previous slide, question. Sure. Sure. So use a shear diagram to find the maximum shear spots. These are places where failure is most likely. And then the second one is you can find the bending moment at any location by taking areas under a shear diagram, if you know a boundary condition. Yeah, so this is just sort of saying in words, that equation and this equation. Running out of time. Oh, okay.
Can I say something? Yeah.
Yeah, please.
So the shear diagram basically is just a shear force diagram. It's not for us to really find the maximum shear stress from the shear force. Now, normally in this bending situation, the normal stress caused by bending, the dominant and the shear stress, we can show some calculation later, is several order of magnitude lower. So the shear force is really not our concern. And the shear stress caused by the internal shear force is really not our concern. The stress level is so much lower. We'll learn about the theory later. So the bending moment, the shear force diagram is just a transition state that we get we have distributed load, we get shear force, we integrate once. We use a method, we get the shear force diagram, and then from the shear force diagram, we get the bending moment diagram. We cannot just jump from I have external apply force, I can have the bending moment diagram. No, we need some transition state. That is the shear force diagram. So you take you check slope, or you have the integration area. So shear force is just for us to get the final goal of the bending moment diagram, but shear force is not for us to find like it will fail at maximum shear force. No, it will not. The stress in terms of failure or not, it's not comparing the shear force or bending moment, it's comparing the stress. And it's very unlikely that in this situation, it will fail at shear stress. Yeah.
But you can, well, we can discuss, okay, I'll stop.
I can show the calculation later. The shear stress caused by this internal shear force is so much lower than normal stress caused by bending moment. So yeah.
Okay. So let's jump to the next idea. Okay, which is that we made this underlying assumption. And where is this picture? There it is. Okay, so we made this. Okay, let me take a step back. So all of this is good and true, provided if we go all the way back to the beginning, that we've got this distributed load WX. And remember, we intentionally selected a spot where there was no concentrated force applied and there were no couples applied, right? That was why I grabbed this spot and not like that spot, for example, in that drawing. In the real world, you have moments and forces that are applied in individual locations. And so how do you deal with those? So this is now sort of taking the equations that we've got and extending them to what if those assumptions no longer apply. And so what we've done here is basically taken that same delta X section, and instead of that distributed load that I had before, this is now just a single force at a point. And this guy is just a moment that's applied at a point, and we'll just do these separately. So and this time I'm going to try to do it right. So so basically the question now is what happens? What happens to the equations if we have a concentrated force applied on CC prime, and then I'm about to put down here what happens if we have a concentrated, no, that's not the right word, but a concentrated moment or a couple, let's say couple, there we go, applied to C prime. Okay, so here we've got that same unit, and instead of that distributed force, we've got a concentrated force. So here's my positive y direction, and I'm going to do my sum of, oh, there's a quick question. So is a couple just two moments on the same beam in opposite directions? Ting's about to chime in.
So let's make it clear. When we talk about force, we have the distributed force, we have the concentrated force, so there's no problem with that. When we talk about bending moment and couple, there's really no like concentrated couple or couple is couple. It is a moment applied at a point or at a cross section. So and for the difference of the couple and the bending moment, we normally say bending moment is the internal bending moment. So that's why we have the shear force diagram, bending moment diagram. It's the internal bending moment. It's more like the internal axial force, internal shear force, internal bending moment. When we talk about a couple means it's the externally applied couple, external applied force. So I can draw it here. So let's say if we have a beam, I climb on this side. Normally, what you learned in the previous class probably is like, if I force applying this way, if I force applying this way, and there's a distance d in between, and this, so yeah, it's d. I don't know how to use this pen. So the couple is equal to the force times the distance. That's why, distance. That's why we say it's couple. But actually, you know that in this situation, it means that it is a bending moment equivalent couple like this. Understand? So couple normally means is a externally applied force on your structure. When we talk about the bending moment, it's normally the internal force. It's generated by what of external force applied. It can be generated by transverse force. It can be generated by bending moment, by couple. Clear?
Can it also be generated by somebody literally twisting at that spot?
No.
Okay,
No.
I have to ask you about that later.
From the twist.
I'll ask you later. I feel like I'll ask you later. This is the fun thing, right? Is see if I can get rid of all this.
You talk about twist do you mean torque?
Yeah.
Yeah, you can. Okay, so let me answer your question first. So if it's a torque, I should have. If it's a torque applied, I need to stand here.
Yeah, you need to stand in the camera.
If it's a torque applied, it's torque it's a rotation about the axial direction. There's no torque in this way or this way. You know what I mean? If it's torque, it's always in this direction. So in the torque, is the shear stress caused by torsion.
Okay.
And it does not cause, it's really nothing related to couple. They're completely different thing.
Okay.
This is a torque. This is rotation. This is twist you're talking about, right?
No. I'm talking about if I grab it here and twist it that way.
That is couple. That is couple.
So I was right, and I probably called it the wrong thing, but the concept is right.
It's couple.
Yeah.
So for the external force applied, you climb on this side, you apply a transverse force, it will cause bending. It will cause the internal bending moment. You apply a couple at the free end or any point cross section, it will cause the internal bending moment inside the beam. But yeah, if the twist you mean is a couple, yes, it's couple, it's not torque. Torque is about rotation about axial direction.
Yes.
There's no internal bending moment generated by torque. So it's only internal shear stress.
So Eric, did that look at what you've done? Did that answer the question? I think we scared him away. I'm gonna go take some other mechanics and materials class where people aren't so crazy. Okay, looks good. All right, thank you. Okay, so let's get back to this. And okay, so as Dr. Teng was describing, I kind of cheated and I wrote out a little bit of the force balance equation, and I need to change this to y because we're talking about the y direction. But I end up canceling out the v's, and I get delta v is equal to that point force F. And so the interpretation here for how we're going to use this to modify our equations is if F is positive, then as we look at this equation, that means that delta V is also positive, greater than 0. And what that means for our shear diagram is that shear force instantly jumps upwards. So it's like a Dirac delta function. And you guys will see in one of the examples. And then the alternative, of course, is that if the force is pushing downwards, then delta V goes the other way, it's negative. And what that tells us is that the shear force instantly jumps downwards. And by the same token here, if I've got this couple that's sitting within my member delta X, if I do my sum of the moments around point C prime, which by the way, this is that point right here. Let me just write this out. It has to equal 0 because we're in a static situation. Delta X plus delta M. And then here's that little added couple. I'm going to do my same little trick of getting rid of all the terms that are similar. And what I end up with is that little add-on couple is equal to V dx minus delta M. And remember that when we're solving these equations, we have to take the limit as delta X goes to 0. That's how the equation was derived. And so if that's true, this term just becomes really tiny, right? We just get rid of it. It's small, 0. And what we end up with then is that just delta M, which is the basis of the equation that we were talking about previously, is just equal to minus M naught, that couple that's added. And so the interpretation here is if M naught is counterclockwise, then delta M is positive and the bending moment instantly jumps upwards, like a direct delta function, instantly jumps up. Oh, I don't know what that was. Okay. And then the reverse is true. So let me see if I can write this across the bottom. If M naught is counterclockwise, let's try this again, counterclockwise, then delta M is positive. And what that means is that the bending moment jumps downward, like a direct delta function. Okay. What's that? There's a mistake. Okay, I'm ready.
So there's a mistake in that one. So we got the equation M that M equal to negative M. Let me write it down. There's a mistake here.
Oh, I wrote the word counterclockwise twice. That should be clockwise, but I'll let you.
No, that's just a mistake.
Okay, I'll let you do it.
So that can I use different color? So
Sure. Yeah, you want green?
Any color. So delta M equal to negative M naught. I really don't know how to use this pen. So if M naught is yes, this is counterclockwise. If M naught is counterclockwise, it means that, well, whenever we have counterclockwise rotation, it's positive based on sign convention, right? So delta M is smaller than 0 because there's negative sign in front. So when there's a delta M is smaller than 0, it's jumped downward. And when it is clockwise, so now M naught becomes negative. Remember our sign convention, counterclockwise is positive, clockwise is negative, then delta M is greater than 0. So it jumps upward.
Okay. Thanks. All right. So now that we've thoroughly confused you, my litany of getting things backwards,
So you can just understand in this way, jumping upward. Well, when you say the delta, back to your confusion about like D to C to D, when we have a positive X direction, it's always from when let's say if we have positive X direction from the left to right, let me stand in front of the camera, and it always everything on the right side minus the beginning, which is the left side. So this delta V is always from the left side to the right side. And when it's upward, it means that your bending moment diagram will jump upward. So the right side minus the left side is move ups. So it's a positive value, you jump upward. If it's a negative value, it means that you need to jump downward.
Okay.
Yeah.
All right. So hopefully, yeah. Got it? Okay. All right. So let me try a couple of examples. So here's example one. See how we do here. So my goal is ultimately to be able to draw the bending moment diagram for this configuration. Again, you guys have taken the class up until this point, and so we won't go through how we come up with the forces and the moments at the boundary, assuming you guys can do that. A kind of key takeaway is that M at A, so the moment at that point, is equal to minus 3p L. And what I want to do then is to create my shear diagram. And I want to create my, this should be bending moment diagram, not boundary. Let's try that again. Bending moment diagram. Okay. And this is going to be the positive X direction, positive X direction. Okay, and we're going to basically look for key locations on the diagrams and use that to construct first the shear diagram and then the bending moment diagram. So on the shear diagram, I'm going to start from basically X equals 0, right? So here's X, and I'm going to traverse to the right, and I'm going to try to figure out what's going on in terms of. Go ahead.
Oh, so I want to add something here. So the 2P, the shear force, and the 3PL there, they are the reaction force we need to calculate at the beginning. It's not given. So it's written here directly, but we need to know that those forces are not given. They are the reaction force at A. You need to calculate. You need to do the free body dominant kind of thing. So the 2P is basically like the force equal in the y direction equal to 0. So we have 2P upward. And the 3PL is basically P times L plus P times 2L equal to 3PL. That's the thing you need to calculate. It's not given.
Would it be positive 3PL if the reaction is going counterclockwise?
You just imagine this way. I have a beam. Let me stand in front of you. I have a beam. I have force applying this way. I have force implying this way. So you can just imagine that you will bend the beam like this. That's why the reaction bending moment is going this direction, not positive. Positive, I said at the beginning, sign convention positive this way, right? So make sure that you are very clear about this, because when you do the shear force diagram minimum, you need to put a sign there. If you don't put a sign there, it'll be wrong. So when you apply a force like this and this beam will bend in this way and in this way, it should be negative. The bending moment on this side should be applied by the wall to the beam, should be in this direction, not positive as you said. Yeah, make sure that this sign is very important because if you get it wrong, the whole bending moment shear force diagram there wrong.
Yeah, just looking at chat, you guys are, yeah, okay. Looks like everyone's answering other questions. So yeah, it is meant to be negative 3PL. Okay, so I'm, thinking about my equation, which is dVdx is equal to Wx, as I'm coming up with a shear diagram, and as I'm traversing from A to C, there's no load, right? No distributed load from A to C. And so what I'm expecting is that the slope from basically A to C, so what we'll make this L, and we'll make this 2L. I'm expecting that the slope is going to be 0. Right, so I'm using that equation to like construct what this diagram looks like. And I know that the value starts at 2p. So I can start at 2p, and I got that from, as Dr. Ting said, the basically mechanics of materials calculation for the reaction of the beam or of the wall on the beam. But the slope is going to be 0. So I'm going to cruise this way until I hit point C, and something happens at point C, right? Which is that all of a sudden there's this point force at that spot. And so if I remember back to this now rather busy slide, if I all of a sudden have a force that's positive or a force that's negative, it's going to create an instant jump either upwards or downwards, depending on the sign of that force in my shear diagram. So here I've got this point force pointing downwards. And so what I expect is just an immediate jump downwards. And immediate jump downwards to what? Well, if I'm farther along and I'm looking at the internal shear force, I've only got one P acting there. And so this is going to just be a single P. And then it's going to continue like that. And then when I get to the end of the beam, well, there's no more beam there to support any load. So it goes to 0. The sort of key points to make here in this example are the way that I got this slope, which is 0, is to go back to this equation and remember that there's no load from A all the way to C. And the way that I got this slope, which is also 0, it is the same reason, right? Is even though there's this point load here, as I go from C and traverse my way to B, there's no load in there either. So those slopes are 0 because W is 0 in those regions. Okay, so let me pause there. And did you guys follow? Okay, at least the logic makes sense. The lecture maybe not so good, but the logic of how to create the diagrams, it's not a disaster. Okay, and so the next thing is to now try to do what the big goal is, which is to create the bending diagram. And I'm gonna, because I already know the answer, I'm actually going to draw it like this to give myself a lot of room in the negative direction. So this is V, this is M. Okay, so same sort of landmarks, right? I'm going to have an L here and I'm going to have a 2L here. And I know because I can do the calculations to find the reaction force on the beam from the wall that the moment at this boundary condition is minus 3 PL. So that's this spot right here. And what I'm now trying to figure out is how I get from that spot to the next big kind of milestone, which is point C, where this force is acting basically at that point. And so what I want to do here is remember my equation dm dx is equal to Vx, and look at my V as a function of X and try to figure out what the slope looks like. Well, the value of V is 2P from 0 to L. And so what I'm going to end up with then is a slope. See if I can draw it straight here. A slope that is 2P. because I'm basically taking it from this diagram and using it to develop the slope there. When I get to point L, my moment goes to just minus PL, and I'm going to have now a different slope, and that different slope is associated with the value of V from L to 2L, and that value is P. So it's kind of hard to draw it, but it's a different slope. I'm not sure if that comes through clearly, but the slope here is just P. And that again goes back to I'm reading the value of V off of this diagram, and I'm using it to determine the slope of this diagram, knowing that I have the boundary condition at the moment has to be minus 3LP at the wall at point A, and at the moment has to be basically 0 when the beam ends at point B, and then just connecting those two slopes with a point in the middle at L. So, questions on how I did that? Seems good. Okay. All right. I think we might have time to do one more example. I know I was supposed to give you 30 minutes and I gave you 0. But
one thing I need to add,
Yep.
because you didn't. So slope is one thing, and remember the conceptual, the second part of the conceptual part. We need to figure out, it's not just figure out the slope. We also need to figure out why this is a negative PL here. And this in the exam, in the homework, you need to give the value here. And this is the second part of the theory, because now the area here in the shear force diagram, you can see that equal to 2PL, the area in the shaded area. That's why we have this delta M here equal to 2PL. That's why this one end up as negative PL. So it's not slope is one thing. Let's make a slope very clear. Let's say this is the, is the eraser here? Anyway, this is the 2P slope, 1P slope. I just want to make the slope difference more clear. From 0 to L, the slope at this section is double the slope from L to 2L. Slope difference, first thing you need to figure out, make it very clear. Second thing, based on second part of the theories, you need to figure out why there's a negative PL. It's because the area. And the same thing, the delta M here equal to PL. That's why we have from the negative PL to 0. Make sense? Both we need to consider. It's not just a slope. Also the value here.
the slope plus the integral, which
And also in the shear force, make sure that when you jump downward, jump P. So we start from 2P, based on sign convention, this is positive 2P. And when the P force applied, we jump 1P force down. So now this end up as P. So make sure that in your homework exam, it's not just about slope. You always need to put this value here based on the area and the either force, external apply force, and that's the for shear force diagram. For the bending moment diagram is the area and the shear force diagram. That's why, back to what I emphasized, shear force diagram is just a transition state for our bending moment diagram.
okay, so that's actually probably a good place to stop because there's only 2 minutes left. So yeah, instead of trying to power through another example. Okay, so
we didn't finish class today. I will change the homework 15 due to Wednesday. Yeah. I will finish the rest example in the next class, on Monday's class.
all right. Well, not too bad for the first time. Yeah. You guys are being too generous. Thank you.